everybody. I'm Alexandria Rivas, and I'm here to explain to everybody how a computer functions. So let's get started with the basics. Um, Here on the right side, there's a diagram of the three main components of a computer: the central processing unit, which is the big brain of the computer responsible for executing the programs by using instructions and input data from memory. Here we have memory, which is physical devices in the computer for storing information temporarily and permanently. It stores input data and instructions for the CPU. And here we have the I/O, which stands for input and output. Devices that take input can be mics, keyboards, touchpads, etc. Devices that give output are screens, speakers, etc. This is what the end user will be working with, how they give data to the computer and how they receive data from the computer. And down here we have different buses. Buses are what connect all three of these components. The data bus sends data back and forth, the address bus sends addresses back and forth, and the control bus sends signals back and forth. So let's see some examples of input devices. We have touchscreen, camera, scanner, mic, controller, webcam, trackball, keyboard, and mouse. And here are some examples of output devices, which we have printer, monitor, headphone, screen projector, sound card, speaker, video card. Here are two diagrams explaining memory more in depth. So on the left side, we can see the CPU actually has its own memory, which we'll get into. It's the cache memory. It's primary storage along with random access memory. These are temporary. So permanent storage is on the hard drive, which is secondary storage. And this orange box represents storage that can be plugged into a computer, CDs, USB, etc. The right side is the exact same thing. It's just a different schematic of organizing it. So we have internal data, which is the blue and green boxes, which is the cache, virtual, random access memory, sequential access, and read-only memory. And then we have the external, which is this orange box, which is magnetic, solid state, and optical. So things you can insert into the computer, add onto the computer. Some examples are down here in the corner. So the main part, or I feel the most important part of the computer, or a very critical part, of course, is the CPU. So let's explain how this works. The CPU is the central processing unit responsible for arithmetic and logical operations. The subsystems are shown here on the right side, and we're going to get all into every single one of it. Let's start off with the arithmetic logic unit, the ALU. This one is this is a very important part of the CPU. It is what performs arithmetic operations for data, which is Boolean algebra, which is algebra that is strictly for 1 and 0 with a base of 2. Add, subtract, and multiplying this, doing the manipulations to the data that it needs to give the proper output. And it does logical operations for the data, true, false, Boolean, of course, and or, and etc., like other things like that. And it works closely with the control unit, which we're about to talk about. So on the right side, we can see how it interacts with memory, the control unit, and how it receives input and output. The accumulator is a register for the ALU, which we'll talk about. So here is the control unit, which works very closely with the ALU. It controls all the activities of the CPU by controlling how data goes to and from the CPU and other devices in the computer. So this is very important. The instruction registers and different registers tell the control unit what it needs to get. So it sends signals and gets signals from the control bus to tell the ALU what to do. So if we go back to the other diagram, we can see how it connects to memory and arithmetic logic unit. And now let's talk about registers. What is the instruction register? So registers are fast memory in the CPU. There's different kinds. I have 5 listed out right here. There's a program counter, also PC is what it is called as well, or referred to as the abbreviation of it. This part of the CPU holds the address of where the next instruction is. So this holds the address, not the data, but the address of where the next instruction is. The current instruction register or instruction register, CIR or IR, is the part of the CPU that holds the instructions that are currently being processed. So the PC copies the address into the CIR to carry the instructions out. The memory address register holds the address of the instruction that needs to be retrieved or that needs to be written to memory, as well as the memory buffer register, which temporarily holds the data that comes from memory or that needs to go to memory. All transfers of data from memory to the CPU, vice versa, go through this. So this is also called memory data register. So this one is how the CPU these two are the main way how CPU interacts with memory. This one's for the data and this one's for the addresses. And the status register, flag register, is when the instruction is executed, the result will affect the status to be set or cleared. So whether it's on or off, 1 or 0, etc. So the CPU takes the status register into thought and will execute the next set of instructions based on that. So this holds condition flag. So if this has a carry flag, say the operation that the ALU just performed had a carry flag, which means you're doing a math problem and you carry a number and it needs to be considered into the next operation. This one will be set. So it'll take it into consideration and add it into the operation that it continues next, and so on. So let's talk about the cache memory that we were talking about earlier in the CPU. The memory that is like actually a part of the CPU. So this is the fastest memory in the computer. I believe it's 100 times faster than random access memory. It is used solely for storing multiple instructions for the CPU at a time. Multiple. The reason being the CPU actually executes instructions faster than it can retrieve them. So it helps overall efficiency. So it helps to have, 4 instructions lined up, for example, for the CPU, because the CPU is constantly blowing through them, Here is an example. Usually there's more than one L1 cache memory in a CPU. Here's a little diagram, the processor, the core, the functional units, registers, and the cache, and how it goes to memory. So, how does the CPU interact with memory? As we explained before with the registers, there's different ways that it interacts with memory. So the CPU and memory interact via buses, of course, because there's no other way it could connect. The data in the CPU needs to be saved in memory is copied and saved via control unit, which we seen earlier, which controls everything that the CPU does. Let's go back and look at it just to be 100% clear. This is what controls where the controls how it interacts with the memory. So the control unit does this by placing the memory address on an address bus, a copy of the actual bit pattern on the data bus, and a write signal on the control bus. So it uses all 3 buses, memory address on the address bus, address on the address, bit pattern on the data, and write signal on the control bus. And right here we can see Step 1 fetches the instructions from memory to the ALU. The control unit tells like which ones it needs and stuff. So control unit is very important and basically like in charge to me. That's how I see it. 2, they process whatever they need to process. 3, they execute it. And 4, they store it back in memory and the process continues. But how does it actually execute programs? Yeah, that's how it interacts with them via buses. But how does it actually execute the programs? So here we can see the first instructions are received and placed in the memory. Then the instruction address is copied to the program counter, the PC. After the CPU sends the address to the memory using the address bus, memory responds by sending the instructions bits on the data bus. So let's stop there and try to explain that. So there's instructions in the memory. So the instruction address, emphasis on address, is copied to the program counter. So the CPU, the control unit tells where, not the control unit, the CPU sends the address to memory so that the address gets sent to memory. Memory looks for it, finds it, sends the data back, sends the bit pattern back via the data bus, and then the CPU copies it to its instruction register to be executed. This is what's going to be currently executed. So once it gets it, CPU runs it with the ALU and yada, yada, yada. So at the same time, the instruction pointer gets to the next address that will be executed from memory. So at the same time, the instruction pointer gets the next address that will be executed from the memory. Meaning, while the memory finds what it needs to, while the memory is sending back the bit pattern to the ALU to execute and stuff, the instruction pointer, which is a register, finds the next address that needs to be executed. And it has to do this fast because the CPU works fast. So here on the right side, we could see fetch the instruction pointed to the program by the, fetch the instruction pointed to by the program counter, add number of bytes in the instruction to program counter, execute the instruction. Is it WFI instruction? WFI means wait for interruption. So the diagram shows that the CPU stops until the IO responds. Like if it isn't, then it'll just continue. But if it does have where it needs some type of signal from an IO device, then it will stop and wait for that interrupt signal. That is what it's called, an interrupt signal. Then it'll idle the CPU. And that's how a computer works. That's the functionalities of a computer. These are my sources for all my beautiful pictures, and my info was mostly from the textbook, also this great YouTube video, and this article about the different registers. Thank you for watching and taking the time to listen to how I explained how a computer works.